Hey class. So today we will be continuing to utilize Dynamo. In this specific assignment, we are going to be building a very simple adaptive component, just like the ones that we've been doing for the past several weeks. And instead of just importing it into our project and controlling the different parameters manually, we'll be utilizing the script that we build in Dynamo to control the parameters of the adaptive components parametrically based upon, in this specific instance, the position of the sun. So based on wherever the sun is within our project, it will either, it will have different actions upon our adaptive component. So this is the same mask that I used in the introduction to Dynamo video. We can use that. You can create a new one. All we'll be utilizing are the outside face. So to get started, just like last time, open up Dynamo. We'll start a new project. And I believe that we have not gotten much into the solar settings, sun settings, within Revit itself. So if we type in sun to our search bar and just go under current, so we're going to utilize the sun settings within our Revit project to influence our script. So this brings in the current settings that are within the project right now. So if we split screen this really quick, down at the bottom left, and I think you've probably done this before, there's a little sun path, sun icon, and this can turn on and off the sun path. So you can visualize the sun path in Revit by just selecting this on. And this little ball up here actually tells us where in the sky the sun is. Now, some of you probably aren't seeing this, so I want to get into how to actually get that sun and get the different positionings of the solar orientation. So if you go under sun settings, under that same sun icon, it'll bring up this window, and we can change the location of the project. We can actually make it Charlotte, so we can have a super accurate. Let's try Charlotte, North Carolina. There we go. Press OK. That brings in Charlotte. And then make sure that you're on a still. Okay. Some of you may be in lighting, and that is always going to be relative to what view you're in. So like sunlight from top left or top right. Still brings in the actual geographic data of whatever city your project is located in, and then you can also adjust the different dates and times of those coordinates. However, with a single and multi-day, you can't control the specific time, but with a still, it captures a specific instance of the sun and allows you to manipulate the different settings of the sun. You can also change the time of year by dragging it back and forward as well as across the day here. And we'll use that a little bit to influence our script. So we've imported our sun settings. So now what we need to do, what we're going to use to influence our project is the vector of the sun. So where is it? Sun vector. Sun direction. So sun direction is going to take the settings in our project, and it's going to give us a vector that we can utilize to measure the angles from our panels that we'll create. And that's just our base. So this is our base sun settings. This is all we need from the solar position. Now we'll get into subdividing our surfaces. So last class we did how to build a digrid structural system. Today we'll just go over how to panelize the system. Now you can definitely go in and divide the surface manually, or you can use the lunchbox add-in that we installed last time and go down to geometry and go to points and then, panel. Go to panel and then you can select any of these different panel types. We'll select the panel diamond for right now. And the panel diamond is asking for a couple things. All right, so it's asking for a surface and it's asking for a UV grid. So basically how many times we want the surface to be divided. So we need to bring a face into a surface into the project from our Revit browser. So we can do select up at the top, select face. Now I'm selecting face. I think I went over this before, but there is a difference between select face and select faces. Select face only allows you to do select a singular surface. Faces allows you to do multiple. So we'll hit select, and we'll just get the the southern facing surface. And if your surface isn't southern facing, just kind of rotate your mass until you get a surface that's primarily southern facing. Then we'll plug that into the panel diamond, and then we can do an even spacing by using a integer slider. Do the drop down to like 10, and then we can plug that in. You can do individual for U and V, or you can do the same like I'm doing. And then we can increase the number of divisions here. Now, be careful. The more divisions that you have, the larger your project's going to be and the longer it's going to take to process. So remember, if you do have a slower computer or your script is starting to get too heavy for your computer, and that you're finding yourself really lagging behind, remember to just hit this manual button. You can build the entirety of the script or the majority of the script and just run it periodically to test it to make sure that your script is running appropriately. So where are we? So we have our panels. So we have our divisions. And what we need now is to find the center point of the panels. And essentially what we're going to do, right? So every panel, I wonder if we zoom out to the 3D view, there we go. And then if we hide the original surface, then we can probably better see there we go, the individual panels. So in this model, what we're going to do is we're going to find the normal or the normalized vector off the face of each of these panels and measure it to the vector angle that is coming off this sun. So this sun's vector angle is coming in basically from the solar position to the center point of the model. We want to take the measurement of the vector coming off of the surface, measure that, and measure the angle between that and the vector of the sun. We get a value, then we can remap those values and redistribute those values to get a number that we can utilize within the parameters of the family that we'll create to create a parametric facade system. I know that was a lot. It'll make more sense as we go along. So to get the center point of these panels, it's a little bit convoluted. Dynamo isn't necessarily the most straightforward or easiest software to do this through, but we need to create a polygon, essentially creating a plane that we can get the center point of. And polygons are generally the only shape, one of the only shapes or elements within Dynamo that you can get the center point of. So if you hit the center and then hit by points, so we're essentially going to take the points that are created, these points on the panels that are generated from this output right here. If we use that, that will create a polygon, and I'm going to switch mine to automatic so get a visual. So that creates a polygon along basically a perimeter curve along the perimeter of each of these panels, and then we're going to use those newly created polygons to find the center point of each of these. Now I'm realizing as I do this that I did forget one step, and I'll show you. I'll get to the point in which that step becomes a little more apparent why we need to take it, and then we'll get back to it. So polygon center, and then what I'm going to do is I'm going to find the normal at point. Let's see if it populates. Normal at point. Yep. So this is going to respond with the normalized vector from each of these points. So we're going to take the center points that we found from the polygons. We're going to apply that to the original surface, use the original surface as a baseline, and then it's going to take all of the vectors, basically the normal at each point along that surface, and give us an output for that. Now, I know I'm saying all this stuff, and it probably, for the majority of you, doesn't make sense. So what I'm going to do is I'm going to visualize what those vectors look like. So if we just do a line in search and do a line by start point and direction length, we can use these vectors as the direction, and then we can just type in 10 as a base length. And with these code blocks, I don't think I went over this. So if you double click on the graph, the node-based workspace, it'll come up with this code block, which you can write your own code, you can do a bunch of stuff, but it's pretty quick to just do a number value. You type in the number and then you hit the semicolon. That allows you to essentially use that as a number. Make sure that you hit that semicolon, otherwise it's going to error out. And then all we need to do for the start point is plug in our center points. And if you look, there you go. So this is visualizing those vectors. So it's essentially getting the perpendicular line direction off of the surface at those individual points. And we need those so that we can measure the angle of the sun along with that. And let me see if we can visualize. I don't know if we can or not. Visualize the vector. Of the sun. Let's see if I can get a sun point. Well, you can kind of see it there. So if it comes back from, if I unpreview this guy, you can see that the sun is coming in from this direction. So all of those vectors, that's all visualizing where the sun is, and then this is going to be comparing and calculating the difference between the solar angle and the angle of the panels. So what does that mean? So we're going to use, delete that real quick. We are going to use the vector created here, and Dynamo has a really, Dynamo has a really nice calculation that you can measure the angle between two vectors. So if you type in angle and then go down to angle with vector, it's going to ask for two vectors. Plug that in, and then we can visualize we can visualize those angles if we plug the angle into the length component. And then if we look at the top view of our 3D view in Revit, you can see that those angles are being influenced by the sun position. And if you click and drag the sun position, those angles will change. And since we have Since we have curvature in both directions, the panels respond based on both the position of the sun within the XY plane or the ground plane, as well as the elevation or the altitude of the sun. So hopefully that visualization makes a little bit more sense, a little bit clearer than the gibberish that I've been saying for the most part. So now that we have that data and we have those, basically all this information that we can use to influence the panels based on the solar position, what we need to do is build a panel that has some sort of parameter that we can then influence. So if we save this guy, save this script in class, and then we can close out of Dynamo, maximize Revit again, and we'll go in and we can save this as well. We can go in, do File, New, Family, and then we'll do a current panel pattern base, just like what we've been doing. And we created a diamond panel within the lunchbox component. We used the diamond grid. So we can select the pattern and do the drop down and come down and select the rhomboid. So it's generally what we're looking at. And then what we'll do, we'll just do a really simple offset. So we'll just have a single surface panel that either grows or shrinks based on a parameter that we set. So if we select the points and then select place 4 points on 2 opposing reference lines. If we select those points, just like in previous iterations, we get a normalized curve parameter, which we can then use and set as an instance parameter. And we need to make sure this is where instance parameter versus type parameters are very crucial, because each panel within our script is going to be influenced in a different way, right? So we cannot have all of these be changing at the same time, which is what a type parameter would be. We need these changing panel by panel. So we can just call this one NCP, press OK, and then we can call this one NCP low. I know I'm very creative with my naming conventions. Press OK, and then based on where these are, make sure that you apply the correct parameters. So this one's low, so we'll do NCP low. And then in our family types parameter manager, we can go in and we'll just use NCP to garner the inverse of NCP. So we just do 1 minus NCP in the NCP low. That way the NCP parameter is influencing the NCP low parameter, and we have a somewhat parametric system based on one input. So if we press OK, then we'll do we'll do a spline through point, select 2 points, spline through points, make it a reference line over in the properties window, and then do that same thing for the 2 remaining points. All right, and then let's place 2 points on those as well, and then same thing, apply those same parameters. This is a low, so we'll do NCP low. The opposite will be just the normal NCP. And then this one, this is also NCP. And this is NCP low. All right, so we have our 4 driving points. Now we're going to create essentially a reference lined border. So we'll do one more series of spline through points, this time with the points that are inside the panel. Just go around, do that for all 4 sides. And one remaining one. Now, if you hover over that, that should select all in unison. If you select it, then hit Create Form. We'll just do a really simple plane for right now. And if we go up to the parameters and start to influence NCP, hit Apply, we can see that it changes based on our input. Now, if you look at 0.5, it errors out, and if we do a lower version like 0.25, it kind of goes back to the same position that it was in 0.75. This is important to note when we are influencing our parameters through Dynamo. We need to know that 0.5 is basically at its smallest. It doesn't exist, and it's going to error out if we do it because there's multiple points in the same position. And we also need to know that basically it doesn't matter if we're below 0.5 or above 0.5, but that's the range of values that we'll have to influence if we want a nice true gradient from one side to the other. So with that in mind, press OK, hit save it as whatever you need to. Solar panel plane, I don't know. Hit save, load into project. All right. So now that we've loaded it into the project, we can open Dynamo back up and go to open the Dynamo script we were working on. Brings it back up. So now we need to import import the family into our Dynamo script. So what we can do is if we type in family points, or family type, excuse me, is the first one that pops up. So this is the drop down in which we'll find our family, and of course there's a lot, so be aware. So I already created this one before, so make sure you select solar panel plane or whatever you named it. And then we need to figure out where we're going to apply these. So if we type in adaptive component by points, so this is going to allow us to take this family, the solar panel plane, and use the points that we created in our diamond panel node to generate those panels. And if you go into Revit, you can see that they are then applied to all of the different panels. So with that, we can then utilize the angles, this information here that is corresponding to the vectors that we visualized before. We can use that data to influence our NCP. Now, how do we do that? Well, we can't use these values, right? Because these are wildly larger than what we need. We need something either between 0 and 0.5 or between 0.5 and 1. So what we can do with Dynamo, and you can do the same thing in Grasshopper, is you can essentially what's called remap or map a series of numbers to a new series of numbers based on a minimum and a maximum. So you take the minimum and maximum of this and you specify a new minimum and maximum that you want this list of numbers to map themselves to and organize themselves to, and then however these numbers fall proportionally into those new domain of numbers, it'll create a list based on that, and you can use that to influence your family. So show that what that looks like. So it's called a map to. Oh my god! If you type in remap, it should pop up. There you go. So map to. Select that. So this is asking for a range minimum and a range maximum and an input value. So the input value is going to be the angles that we found with our two vectors. So we plug that into input value. Now, the range min and the range max, that's asking for the minimum value and the maximum value of this list. So there are two components that you can use. One is minimum item, the other one is maximum item. Just type in min, max. All right, and you plug that original list into both of those, and it's going to give you the lowest and the largest value within that list. You plug that in here. And then it's asking for a target minimum and maximum. So our target minimum and maximum are from our NCP, and we want that to be either 0 to 5 or 5 to 1. And so we can specify that by using a number and specify, so we can use 0 as our, actually let's use 0.51, because remember, if it's exactly 0.5, it's going to error out because all the points converge on the same place, and it won't create that surface. And then our final number will be 1. That'll be our maxed out panel. All right, and so what this does is it takes this value of numbers, it asks for the minimum maximum. So the minimum of this list is 15.4 and the maximum of this list is 124. And it basically says, all right, the new list is, the minimum is going to be 0.51, the maximum is going to be 1, and wherever the remaining numbers in this list fall proportionally within that domain is where they're going to be remapped. All right, so this list is basically a proportional representation of this list just between those two numbers. And then we can use this data to influence the panels that we created up here and influence our NCP. So the way we do that is set parameter by name, set PA. Make sure it's all one word, because for some reason if you do it outside, it won't search correctly. So this is going to set a parameter within a family based on a value that we input, right? So if we plug this in, so it's asking for the Revit element, which is our adaptive component. It's asking for the parameter name. So how to input words in Dynamo is with a string. Might have covered that in the last value, but our string is going to be NCP since that's the parameter that we're influencing. And then before we plug this in, you know, we can go in and plug in any value that we want between 0 and 1. So if we do a number slider and we do between 0 and 1, and let's say our step is 0.001, if we plug that in, it's going to influence the whole series of panels, right? So we can control all these panels based on the number slider that we just created. All right, but we want this to be parametric to the sun. So instead of doing that, we can take our newly remapped numbers, plug that into the value, and this might take a minute. And then if you look, And we can probably go in and hide the visualize. There it is, the start point direction length. If we hide that, of course, for some reason it's not going to hide it here. But now our panels are being influenced directly by the sun, and it looking like it's doing the opposite of what we're doing, right? Like if you had an actual facade system on your project, you'd want the panels to be the shading panels to be as large and as opaque as possible when it's in the direct path of the solar radiation, and you want it to be open in non-direct sunlight. So what we can do is we can switch these numbers, and it does the opposite, right? And let me see if I can turn the shading on, visualize this a little bit better. Kind of does, not really. But yeah, and if we take the sun and we manipulate it across the sky, does that work? God, I really want to turn those vectors off so you can see the thing a little bit clearer. Oh well. All right, so and you can see that as the sun moves, our panels react to it, and we have a fully parametric facade system that reacts to the solar location. All right, so for your homework assignment, all I want you to do is add an additional parameter, create a new adaptive panel component. You can reuse ones from earlier assignments and manipulate them using the same script in different ways in reacting to the solar position. I'll lay that all out on Canvas, and yeah. Hope this wasn't too confusing. I know trying to explain scripting is a little challenging, so I hope once we visualized it, it all made sense.